what you say, useful or a flexible condition that traditional approach will be giving you. But what is the pitfall or drawback for this approach is that any minute change, it should be redefined. Total table or total design has to be re-evaluated. That is a tedious process. Like if the number of states are more, then the system handling by the traditional approach, where we need some sort of changes to be accommodated in your designs, so as to improve your efficiency parameters, or so as to improve your speed parameters, or so as to improve the system overall performance, then we need much of changes. Okay, in one step, no design will be concluded to a product level. That is the one rule what we have. So we need much more iterations for a design. Many steps has to be repeated until a satisfied output is coming. So that is what related to your traditional approach. Maybe some extent this problem can be overcome by the second method what we have seen, that is multiplexer method. Something like here, your mux will be able to accommodate the number of states as the inputs to the muxes. How many number of states you have, that many inputs we define. Because each state, one input it will be defined with. And when we select the state variables, this becomes the selection lines, A, B, C, and so on. Based on which state you are in, that defines what should be your value, or what should be the next state your design will be going to. Okay, this happens to be the lookup sort of thing, a derivation of lookup table. And what is the relation, or how many number of muxes that should be used is, it relates to how many number of states you have. Okay, that means say, and you have 4 states, 2 state variables you are taking, means each state variable will be using one flip-flop. Yes or no? If this is your setup of the designs what we take. Okay, each one variable will be taking one flip-flop. And what is the size of the mux here to be added? Not only this flip-flop, here this path we will be adding one mux in mux method. Okay, what is the size of the mux will be defined by how many number of states you have in the design. Because each state will be provided with one of the input to your mux. Okay, so some sort of flexibility that we can have is, if you are taking a size of n is to, sorry, maybe other name we give, p is to 1 mux. P happens to be the number of inputs now. Now, any change or any increase, like this P indicates the number of states now. P indicates the number of states. Okay. If how many states this can mux can handle is how many number of states you have, or what is the size of the mux you are considering, that many number of states it can handle. So to the max P number of states, P is to 1, that means say 4 is to 1. If you take 4 states it can handle, you take 8 is to 1 mux, say. Here number of selection lines is 2. That means your state variables will be 2. And here 3 selection lines. So 3 state variables and so on. That means, see here, how many number of state variables you have, that many number of D flip-flops and that many number of muxes will be used. Because a pair of mux and D flip-flop will be used in this path. Okay. And the size of the mux is dependent upon how many number of states are there in your ASM. Number of muxes is equivalent to the number of state variables. The size of the mux will be dependent upon the number of states we are saying. So any state, like any number of states more than 5 to 8, you'll be taking 5 to 7 or something, like if we are taking that from 1 to elements, 1, 2, 3, 4 sort of thing, 5 to 8 states, your 8:1 can handle. 9-state system needs 16:1 mux. In this, how many will be vacant? 9 will be used out of 16, and 7 more vacancies are there in your mux. Yes or no? So 0 to 8 you are using, and 9 to 15, these are vacant. 9 to 15 are vacant. That means that few more states you can add. If you are taking the mux method, okay, if your original ASM is having say 9 states, we are in need of 16:1 mux. Okay, and this 16:1 having how many number of selection lines?
4 selection lines.
4 selection lines. Out of this 0 to 9, already your original ASM will be using. The remaining are vacant for us. Any modifications to your ASM, if you want to do any addition of the states you want to do, there is flexibility. Only try to derive only these added state equations. Because we were dealing this as, say, if this is related to a flip-flop, a variable. We were saying A0, A1 and so on to A7 sort of thing. Yeah. Likewise, you derive A8 to A15 sort of thing. Okay. So that is the flexibility you are having. But coming to the limitation thing, see here, these are directly related to the number of states we are seeing. Say, in the market, 32:1 is the available your commercial mux we are saying. That means 32 states you can have in the ASM. But imagine what is the complexity of the design if that ASM is having 32 states. It's very huge, huge, unusual size. Actually, we don't try to take that many number of states because we are taking that in top-down approach. We try to cut down that to some manageable 5 to 10 states only. More than that, what happens is your decision making or your paths or your analysis becomes very clumsy, and maybe there is a chance of skipping of some of the conditions. Okay, that things may happen. So we try to cut down that, try to take something like to the max of 10 states. So 32:1 is the maximum number of states. That means that 32 states you can handle using this mux approach. Okay. So taking these advantages and disadvantages, now mux also, though it is very advantageous compared to your traditional approach, one more approach is proposed or suggested in place of multiplex method. That means it is left to the discretion of the designer whether they have to choose a traditional approach or mux or one hot or ROM based. Different methods are proposed, different methods are floated. Now it is left to the discretion of the designer which method the designer chooses for their design. Okay, this one hot is the name itself says always one to be on. One hot means always one to be on. One hot method or one hot synthesis. if you remember, in your Mux method, we were deriving the table in terms of this, present state to next state and what was the condition. That means all these are the transition of outgoing arrows. Outgoing arrows. This is layman way of remembering. Outgoing arrows. Uh, Maybe this we don't say it as technical thing, but a layman way of remembering. Mux method is deriving all possible paths of outgoing arrows. One hot approach is the reverse one. That means we try to take one hot synthesis is incoming arrows. Don't say this is technical thing. Only for your ease of understanding, I'm giving this. And naturally, this will be different or what you say, reverse to the method of your Mux method. That means when this next state will happen and when the present state is so and so and what is the condition. Previous it is present state versus next state and what condition the transition happens. So let us take okay. So we are taking an ASM having 4 states, PQRS having 4 outputs defined, 2 conditional outputs are there, and 4 unconditional outputs. Okay. So here in one hot, we are saying the incoming arrows. When the next state will be P. Incoming means this one. When the next state will be P, that means something coming from other state, it is reaching P. Okay. So when this next state will be P is when the present state is R, see here this path. When the present state is R, the next state will be P on the condition that X being true. Okay. And when the present state is Q, see here, when the present state is Q, and on the true clock, because there is no condition or test variable on which we are testing for. Okay, whenever the true clock is happening, the transition happens. And S, the present state is S on the condition that Y being true. So how many incoming arrows you have, that many equations you will be getting, or that many present state conditions you will be seeing here. So 3, 1, 2 and 3. So 3 conditions we have given here. Next, Q you have only one state. See, we are not taking here as if you see the state variables, we are not defining because we don't need to define it now in this approach. Okay, so when your next state will be Q, give an attempt now. When the next state will be Q, when the present state is
Present state
Present state is P
with
and the condition is W.
condition W.
yes, only one incoming arrow. Is it only one incoming arrow?
We can have another
No, ma'am.
S
S
and
and
Y
Y dash.
false.
Ma'am, yes, when why?
Yes, when the present state is S and Y is false.
Y
So
dash.
two incoming arrows. So 2 conditions we defined. Next, R. R is having only one path, I suppose, only one incoming. When the present state is P and W is false. Correct?
Yes, ma'am.
Yes, ma'am.
And for S, you have only one incoming. So when the present state is R, X is false.
False.
Okay, check out whether all the outgoing incoming arrows of each state is defined or not. Okay. Hope all the incoming arrows are defined. P has 3. Done. Q has 2. It's done. R is having 1 incoming. Complete. So S is also having only 1 incoming. Complete. Now the equations here to be derived is, what is the next state? When the next state of P will happen? When the next state of Q will happen? When the next state of R will happen? When the next state of S will happen? So we'll be deriving these equations such that it is the combination of the present state and that condition put together. That means AND logic. When that is in the present state of R and the condition of X being true, this will be the next state P. Or when the present state is Q on the true clock. Or when the present state is S on Y being true. Any of these conditions satisfied, it takes the next state of P, or your design will be going to the next state of P. Okay, the same way, next state of Q will be happening when the present state is P with W conditions satisfied, or S with Y dash. That's all. 2. Next. Next state of R is PW dash. And next state of S is Rx dash. And what about the equations of the outputs? Out 1, state P. Out 2 is state Q or state S, Y. Out 3 is state R. Out 4 is state S or state P on the condition W being false. These are the equations of your outputs. Okay. Maybe if we need to put this into our combinational logic element, directly you can take this from each flip-flop, or you may take the AB values. Both are acceptable. Let me take this. Like, how do we implement this? Is how many number of states we have, that many number of flip-flops are needed directly here. How many number of states? Now we are not speaking of how many number of state variables we are taking. In your Mux method and traditional method, we had AB, or what you say, the state variables coming into. But here, direct how many number of flip-flops are needed is directly related to how many number of states we have. Here, 4 states we are defining means we need to have 4 D flip-flops. Each flip-flop corresponds to 1 state. Okay. This one is your Q of P, and this one is Q of Q, Q of R. This is Q of S. Q is your output of the flip-flop. Okay. And this will be D of P, D of Q, D of R, D of S. And this circuit should be synchronous. So your clock will be common system clock. And there is one more parameter which also has to be common, is your clear. There is a much important role of this clear signal here. What is that? Okay. So clear and clock are common. Now, what are these equations? How do we define this? Is we need to derive this something like with AND or logic sort of thing.
Excuse me, ma'am.
Yeah.
Ma'am, I have a doubt. Ma'am, in the table you made above, like from in the P's equation, like we have from state S, if Y is true, why aren't we writing that it goes to O2? Like sorry, the state R, as it's a conditional block there, right?
No, I couldn't get. In state P,
In state P, we have written that if the next state P is P and the present state is S, the condition for which it goes to next state P is Y. But in the diagram, like the lower part of the diagram, we have seen
why
that.
is not state? No. I could get your point. Why is not state now?
Sorry, status variable.
This is
For the status variable Y, when it is true, why aren't we writing that it goes to the state O2? Like the conditional block is there, na, in between O2. Why aren't we writing like that?
that is not state. This is a conditional element. Okay. What happened? This is conditional element now. This one indicates a conditional output. It's not a state. An output of the system. Something like, say, what is the exact transition you have is, say, this one. From this point, if you start, okay, based on the condition, this is your one state to another state. This is your ending point. Okay. The other path is from this point, if you start, this is another state transition. That means from state S, you have 2 other states, stable states to which it can reach. This statement, okay? You have,
Yes.
see, wait. S has, from S, you have two other states where it can reach, the state Q or state P. When it is reaching state Q, like the condition of Y, if it is false, it will go to state Q. Okay, that means here when your machine is in state S, what are the instructions that are given to the system will perform the iteration, it will generate out 4 and it will generate a value of Y and that Y will be tested. Okay, if the generated output Y is 0, that means false, it will direct that to state Q. If that condition of Y is true, what does your design or what does your hardware need to do is generate an output to 2 before it settles to a stable state of P. This is the transition between two stable states. What are all the other paths you are mentioning, whether it is a test condition or generating a conditional output and all? This is in between iterations that your design will be performing before it reaches another stable state or a new stable state. So out2 is not a stable state. It is a conditional output that will be generated based on the value of Y, based on the condition of Y. If Y is true, it will generate output to 2, then it goes to stable state P. Maybe you are getting confused or you are confusing yourself saying that out2 is a state. Out2 is an output that will be generated when your design is in that state. That makes a difference there.
Okay, ma'am. Now I got it. That was the only doubt, which you mentioned right now, right? The confusion was the doubt. Okay.
Yeah.
Thank you, ma'am. I got it.
Excuse me, ma'am.
Yeah.
Ma'am, I have a doubt in the output expression, ma'am, in O2. So O2 state will be attained when it is in the Q state and or when S state in the condition Y becomes true.
Yeah.
Ma'am, it can be attained, O2 can be obtained even from P state, no, ma'am, under the condition that W is true.
Which one? Which state?
Ma'am, O2 could be obtained from P state also, no, ma'am, when W is true.
No. Again, the same confusion. See here, this state and this state. That means you're okay. From this is P is one stable state, na? And Q is one more stable state, na? Yesterday I said when two stable states are there, the first stable state will be related to that clock that will be initiating that state iteration. First stable state, say between P and Q, I can take this as the first state and this is say second state. Okay. When I start iteration here, I apply a clock. Say that clock be 1, say. The first clock relates to generating output 1 by the instructions followed on to your hardware. Not only that, generate a value of W. Okay. And this W, if it is true, then it will make your design to reach only Q until Q. Here that clock stops. The function of the clock stops here. Okay. And for getting an output, say the other path is that if W is false, in the same clock, the output 4 will be generated because a condition of W being false is indicating that out 4 is conditional will be generated and it makes the design or your hardware to reach the state R. So here the function of clock 1 stops. So this is the stopping point for clock 1. For the next clock, for the second clock or after completing this clock, maybe if you name this as clock of P, for clock of Q, if it starts, then O2 comes out. Then see, in the same clock of P, we may get only out to 1 or out to 4 based on the condition of W. Got this? By default, out 1 will be happening. But out 4 will happen on a condition of W being false. Okay. But for generating a output which is indicated in a stable state, it needs its clock. Another new clock applied for this will generate output. Not that this will be generating the output. I think yesterday also I said this, between two stable states, if you consider only one stable state, that means where your clock is initiating the iteration, will be making the design to reach another stable state. That point your clock function stops. What is the actual meaning here? If you can put this into a clocked format, we can explain this. See, first clock, if you apply, this is your clock P. I can take this as clock P. In this duration, your P state should be going to, when at the end of this clock P, this P state will either end at Q or end at R based on the value of your W. When W is true, it will be at Q. When W is false, it will be at R. Then that function of the clock is over. Now, if this is in Q, this becomes clock Q. If this state is going into clock, that means state R, that becomes clock of your R. So again, your iteration, if this is your clock Q, where it will be going, there is no other condition to be verified. When it when the clock goes from your off condition, before it initiates the another clock or something like in this duration, I'm strictly saying this duration only, every iteration completes. This will be a latching mode. This will be a latching mode, no? This we have seen in the earlier classes also. Your Q will be taking that, it will be taking that to next state of P. Okay, so earlier P state, if it is reaching R, this duration becomes the clock of R. When this is clock of R, by the end of this clock, based on the condition of X, if X is false, it will make, or it will take the transition from R to S, or if X is true, it will make that R going to P. That's all. Stops here. The next iteration of P or S, is for the next clock. That means here for one clock, what is the function or what are the operations that will be performed is generation of the unconditional outputs, completing the iterations that are instructed, testing any test variables if they are there in the path, generating the conditional outputs if they are there. That means all the functions that are mentioned in the loop or between two stable states will be completed. Is this clear?
Yes, ma'am.
Just a second, I'll come. Just a second, I'll call. Yeah. So is my point clear? A question of whether your output 2 can be generated from state P.
Yes, ma'am.
No two stable state outputs will happen in the same clock. That is a blind point you can remember. No two stable states will be generated in the same clock. Only one stable state. That means the maybe you can say that where from the clock has started, for which state it has started, may at the most take that to another stable state, generating your conditional outputs or testing the test variables or generating the unconditional outputs. So in state P, out 1 will happen or your out 4 will happen on the condition of W being false. And makes it the state P go the transition of state P to Q or R. That's all. Out 2 happens for the next clock. Okay. Still doubt is not clarified?
Yes, ma'am. I understood, ma'am.
Okay. Now here how we'll be connecting these fellows is we try to take this as say R and X, Q and T means this will be clock. The clock system clock what we are taking, this will be connected here. Okay. And this will be SY. Okay. And see where from this P, Q and S comes is from this point. That means say from this point it should be connected here. It becomes very clumsy if we draw this. Faulty. In order to avoid that, what we do is only for the first flip flop we make it as active low and make the circuit output as active low. This will be making it logically to be true. Remember that mixed logic approach of analyzing the designs. Remember them? Still you remember the mixed logics or forgot? Logical tree. Huh? Remember?
Yes, ma'am.
Okay. So whenever we are trying to tie one of the output to another input sort of thing, logically both the levels has to be true. Levels in the sense the truthness has to be mapped. That is what we call it as compatibility of the levels. So what is logic high? If I try to make it logic low, conveniently I can make this active high as active low. That means when this design will be initialized or starting, making sure that P is the initial state is when the first state is made as active low. This is the one biggest drawback of one hot approach. Initialization problem. If it is not properly initialized, that means if it is not starting from state P, it will be starting from any other state rather than P. What happens is for every iteration, for every clock, your performance or the outputs of the design will be completely different from the wanted outputs. Where we need P, we get Q or S or R. Okay. And once you start this operation, that means once you switch on the design, here if you see, we are defining something like next state versus present state. There will be always one state to be true. Always one state to be true. That's what we are saying. This is one hot. Always one of the output will be true. Based on that, your condition there will be a continuous change of one state to the other that will be happening. And if you want to stop the operations, only possibility is that you can either totally switch off the design or switch off the circuit, or you can use a common clear statement here. This common clear is used for that. First is making sure that no other state is switching on at the initial state except P. In order to ensure that we try to clear all the flip-flops before applying the on signal, initialization. And once you start operation for stopping, we need to use this clear only, or we have to switch off the design, or we have to switch off the power supply to the system. That is the two major drawbacks we have. Something like initialization problem and switching off or stopping the iterations. We need a clear statement. But the other way is that any number of states you can include. Only the thing what will be adding is for each state, one flip-flop will be getting added. Any number of states you can add. Okay, 10, 20 states also you can add, but what is the complexity that will be increased is the number of flip-flops into your designs gets added for each state, because this is directly related to the number of states. How many number of flip-flops you are to, putting in. So your overall circuit looks something like this. This is your path. This is your path, okay, of your feedback path, and where from like the other portion where we define this outputs is combinational logic with your WXY out 1, 2, 3, and 4. Okay, and from these fellows, from these things, these PQRS will be connected here. PQRS. These will be connected to these points. Okay, the combination of these will be deriving your next states of your what you say, next state of P, next state of Q, next state of R, and next state of S. So these equations along with this will be implemented as a circuit here. That means this segment and this segment as AND or logic will be accommodated in this hardware setup, and these D flip-flops will be coming here. Okay, so this will be connected to this. So this will be the connections I'm taking. Able to understand? Little bit you flip this and you can visualize this. This Q of P, Q and R and S will be coming here. These inputs of the D flip-flops will be taken at this point, and this circuits will be accommodated in this portion. So which one is flexible compared to your mux and one hot? Which one you feel that it is flexible or more convenient to handle? As I'm saying, this will be like based on the discretion of the designer. We are saying how many states your design you have, what is the complexity you are handling, how many number of states you can easily access or you can maintain. Okay, there the number of flip-flops are less. In your mux method, number of flip-flops are less because you are taking 2 powers of the things. No? The 2 powers of how many number of flip-flops you are taking will be addressing that number of states. But here in your one hot, the number of states directly relates to the number of flip-flops you are taking in. The flexibility in mux method is that you can add more number of states until the size of the mux is not exceeding the input, how many number of inputs it can handle. Whereas in your one hot, you can add any number of states. Only the thing is you will be adding the flip-flops. So complexity of the design goes up in your one hot if the number of states are more, because direct flip-flop means your cost of the design will be little bit more compared to your mux method. But what is the flexibility is that you can add more number of states into your ASM conveniently. But what is the major drawback of your one hot is that the initialization problem is there, as well as stopping of the iterations. It is also a problem. Two pitfalls you have, or what you say, two disadvantages you have. Okay. So that is left to the designer's choice now. We can't say that mux is having disadvantage or one hot is having disadvantage. Both have their own advantages and their own disadvantages. Okay, so this is one approach we have seen. So any doubts you have? This approach, any doubts you have?
Ma'am, could you please explain the part? I have understood that after if QP is gone wrong, everything goes wrong. Until that part, I have understood, ma'am, but not this part, ma'am.
Which one?
Where one we will be integrating all the part. Yes, ma'am.
This one, huh?
Yes, ma'am.
Okay.
Ma'am,
Actually,
explain from that P part also, ma'am. Why did we make it complement and connected?
this one. Okay.
Yes, ma'am.
Okay, actually, if you take this representation, when any input we try to define this is active high now. one logic is on and 0 volts will be off. This is for positive logic. Is that okay?
Yes, ma'am.
For positive logic, if you are putting this way, it indicates that a voltage of that means logic 1 means say 5 volts if you are giving, that makes that terminal to be on. Okay, so here what we are saying is whenever we switch on the system, or any what you say unwanted spike is happening in your design. Spike is nothing but 0 to some 5 volts or plus or minus of this value. A abrupt increase in the voltage may gives a false indication to this design, which is positive logic, as switching on the flip-flop or switching on the circuit, where it is a noise. Actually, this is noise. We call this as runt signals, runt pulse, abrupt change in the inputs. This will be happening whenever there is a spark in the design or whenever there is a false abrupt increase in the uh, circuit potentials values. Okay, so that is one point. So now what we are taking here is all these fellows, every flip-flop, if I indicate that in this form, it indicates that it is all active high, means that 5 volts will make it on. Okay, and but one condition what we are saying is initial state should be P. Your design or your system should never start with any other state rather than P. Okay, and if this P has to be like made assured that only with P your system starts, is that I need a provision where intentionally if I give a wanted value, then only it will start. Okay, if I give a wanted value, then only it will start. That condition, or if that provision is given, that then I can make sure that only from that condition my system will start operation. Okay, so what we'll do is the one which we want to start, from which state you want to start, only that flip-flop, instead of making it as a positive logic, we make this as negative logic. I'm saying I'm taking this fellow to be on when it is 0 volts. When this is 0 volts, you remember this, where we don't take them as active high, rather we take them active low. You remember them? Enable signals. Any design enable signal will be your active low. What is the reason? Because any abrupt or any false potential that is happening on the design should not be enable the design falsely. Intentionally, if you give 0 volts only, it will be enabling the overall circuit. That is the concept. The same concept we try to use here. I give intentionally a 0, then only it will start operation. And if it starts operation from this point, it will automatically generate the value, or what you say, the next condition of P based on the condition that is existing here. The condition that is existing here. Combination of this condition with your WXY, these are your test variables, will decide what will be the next value of P, or when you will be getting the next one. See, actually, this circuit, if I need to redraw this, I should put this in this format. This will be D of P, D of Q, and so on. Okay. And this will be giving me Q of P, and this is Q of Q. That means P, Q, R, S, and so on, each flip-flop. And you'll be having the test variables W, X, Y. And here you'll be having your out1 to out4. And here, see, here we are defining this set. Now, this will be generated here with the logic, this block connected here. I'm taking this as a block. This circuit will be connected here according to the values existing here. Now, this will decide what will be the value of P. Okay, and this circuit, one more circuit, you connect them here and you will be defining that connectivity which decides the value of next value of Q. That means this portion you are reversing. You are flipping that and giving the connections here. Now, wherein here we make this only this fellow to be active low. This one, active low. That means only if I make this as active low, when this value is 0 volts, it will start the iteration. Then always there will be one true condition happening. It will drive to the next state. It will take to the next state based on the logic of the values that are combined here using this circuit. We are using this circuit to define the combination of the present state and the existing value of the test variable. So these are the test variables available. These are your what you say, the present states. No, for the next clock this becomes the present state. No, the present state and the present test values, combination of these two according to the connectivities you are defining here will decide what will be the next state. Got this? What will be the next state will be decided by the combination of the next. Who will be deciding these values? The previous clock. These are the previous clock responses that you have achieved at this point. At this point. Okay. Say if you are taking this for clock is equal to 2. Okay. This will be the responses when clock is equal to 1 at this point. This will be updated, no? The updation of this happens for the next clock, no? When we have started the sequential designs, we said the relation between these values and these values, small y and capital Y. The responses or the outputs derived at this portion will be for the previous clock. And if you take this as the present clock, this present values will be updated for the previous outputs happening. The present clock, this updation will be happening for previous clock responses here. Okay, that defines a continuous iteration or continuous shuffling of the states between PQRS. Continuous shuffling between PQRS. And see, this P and this P, what is the difference you have? Same clock you'll get or different previous clock and the present clock you'll be having. Q of P is nothing but the same P what you are tying here now. But the value of P that is available here will be for the previous clock P value, and this is for the present clock a new value that you get. And this P will be getting updated here for the next clock. Yes or no? the values of PQRS, whatever you are tying here, will be the previous response of the system or previous clock generated outputs. That will be updated for the present clock. Able to understand, able to give the clarification.
Yes, ma'am. Ma'am, here the negative logic will make sure that the system will be in state P whenever the system is switched off, right? It will make sure that it will go to the state P.
Whenever we are starting to operate, it will start, it should start from P.
Okay.
Intentional 0 we try to give, and then the iteration will continue based on the conditions of your W, X, Y along with PQRS. That
Okay.
means, see, once you initialize this based on this P value, this updated P will be available at other levels also. See, P here, you have here also. P here also you have. And wherever, okay, only 2 states. Say, if based on the next state of P here, when updated thing, if you take back here, whether W is true or false will decide whether your next state should be QRS. Got this?
Yes,
For
ma'am.
the present clock, you are defining P. Okay. This will be your next state. And this, along with the conditions, here you have test variables. Now, the test variable value, based on the test variable, that will decide whether from this present state of P, it should go to Q or it should go to R. That's why we are taking a combination of the conditions, condition and the state, condition and the state together. It will decide what should be the next state. And see here, R you have here and here. At this state of R, when this is getting updated for the next clock, that R condition along with X is evaluated. When R present state is R and X is true, it will take to the next state of P, else it will take to the next state of S. That means always there is one next state iteration or next state transition condition available for us. From the present state to the next state, it will take the transition based on the combination of the present state and the test variable value. So that combination will decide what will be the next state or what will be the next transition. So this is a continuous process. There won't be any stopping there. Where do you stop? Say, once you initialize that your design starts from P, always there will be one condition true, no? Any place you take, there will be one condition that will be true always. That means the transition will be between PQRS based on what is the what you say, this path you are defining. This is the path, no? These are the paths you are defining. To switch off or to stop the iteration, only this reset, this we call it as clear, the synchronous reset will be used. Synchronous reset. This is the synchronous reset. Clear condition. Using synchronous reset only, you can stop the iteration. These are the two drawbacks we said. Yeah, still any doubts? Maybe one or two examples will do, then you will be getting more clear-cut idea. Okay, if no other queries, I'll stop the session.
Excuse me, ma'am.
Yeah.
Ma'am, can you take one query session? Like right now, it's fast time, but can you take a query session about the mini project? A lot of us have doubts regarding that.
Yeah, tomorrow we will have. Tomorrow.
Like about the mini project. Like we are not getting the specifications as to what qualifies as a mini project and what all do we have to do. Like there are many queries in our mind. So like I hope other students also have, but in our group specifically we have.
Okay, you can ask now if you have any like idea that you are thinking of.
No, ma'am, we were looking for the ideas. Like we wanted to start for looking for the ideas, but we were not getting where to start. Like, uh, means we were getting a lot confused right now about this, where to start and.
See, you can do this now. The uh, mm, project ideas using VHDL and Verilog, you can browse. Project ideas for VHDL or Verilog, you can browse and see.
Ma'am, in that, like we did try to search for that, but in that, what qualifies for the mini project and what goes beyond that? Like after.
Experiment sort of thing won't be considered as a mini project. Simple experiment means something like a single in, a single out sort of thing. A control of temperature, say a temperature control of a room. That qualifies to be an experiment, because only one parameter you are taking, which temperature of the room is your parameter, and you try to take the assessment like whether the temperature is below the reference or above the reference, and you will increase or decrease. There is only two controls you have now. That becomes a simple experiment. Whereas if you take say automatic control of the appliances sort of thing. A simple example, let us take. You have an appliance of say a fan, light, AC, and automatic closure of door. So some parameters you are taking. That means here you should be using what you say, the count of the persons entering or leaving, whether the fan should be speed of 5 or 4 or something like that, a speed range. Then light means intensity, based on how many people you have. Do you switch on all, say 4 lights are there, 4 to be switched on, or only 1 to be switched on? That control of 2 or more gadgets having 2 or more different parameters of adjustments. And automatic closure of the door, say if you take, you need to have a sensor at the door point where it will count the number of people coming in one direction and going in the other direction. Say entering direction, you'll count up, and leaving direction, you'll count down. So you'll be using a counter there. Then controlling of the lights means you will be having the intensity adjustment based on the count of the people entering. Okay, that means you are relating the counter logic values with your light controlling thing. And same way, whether the room temperature to be cool or hot, whether you have to switch on the fan or AC. That means your work should be related to something having multiple controls or multiple what you say, judgments to be done. Instead of having one single parameter, you can have multiple parameters. So that you put it as one single design, it becomes more complex. You have many components coming in there. You will be having the selection multiplexers, you will be having the counters, you will be having the sensors, everything in a one packet. That becomes a mini project. A simple
At least 4 to 5 parameter. Like you mentioned, minimum 2 parameters should change. Like the parameter count should be 2, right?
parameter means it depends on what is the complexity of the idea also. Say encoder, decoder is there, encryption, decryption is there. Encryption, decryption is there. FIR, IR filter elements, if you can implement. It becomes like, it depends on what is the idea. Based on the idea, okay, one or two parameters is having much complexity, or based on the idea, how many parameters you can control. All that, like, that is something we cannot fix. Saying one idea will have only two parameters or one idea will have four parameters. It depends on what is the logic you are taking.
And ma'am,
Should not be,
regard
see, a clear-cut thing is, it should not be as a simple experiment. Like we listed in the experiment now, this list, a counter, an adder, a simple clock. If you take clock is a age-old, what you say, an experiment sort of thing that every student will be doing. Entertainment electronic sort of thing. Watch means seconds, minutes, and hours counting. That becomes a simple experiment. We don't accept that.
ma'am, regarding the abstract, like we have to write a paragraph or something in a Word document, and we'll be submitting that, right?
Yes.
And you will be giving, once you give like a confirmation that yeah, this project you can work on, then we have to start working on it.
What is that we need for assessing is that you need to explain your idea in a 4 to 10 sentence format, and what is the corresponding circuit diagram or the flow chart sort of thing. Any flow explanation or circuit explanation is needed for that. So based on that, we decide what is the complexity of the design. Just giving a 4 to 5 line explanation also, fewer times we may skip the complexity. You need to give what is the size of the circuit, like what is the how many number of blocks you have in your design, how many components you are using. That sort of assessment is needed. So either a clear cut circuit sort of thing, or clear cut flow or block diagram sort of thing. That
Okay,
is
and in the when like whenever we will be submitting this mini project, we have to like create a presentation or something for the project, or like normal we have given it in the abstract itself, right? So like
no, abstract speaks only the superficial content of your work, but your total presentation will speak the stepwise implementation, stepwise what you say, the clarification regarding your functionality of the segments.
okay, ma'am.
So
Okay,
something
ma'am.
like something you can take this format. Say you want to have a control of the lift. How many parameters you have? Maybe in description you will say that you want to control the lift for moving in up and down direction. That's all. But actually coming into the practical aspect, we need to say the number of people entering, what is the total weight of that, is it exceeding or like which floor it has to stop first, who has pressed one or who pressed two, or if it is 20 floor the thing, like it becomes a person at fifth floor is asking for the lift to come up, and some other guy at the second floor is asking the lift to go down, say. To whom the first priority has to be given, that judgment has to be done, no? So we need to develop a control logic there, whether the first operation of going up, lift going up to be given access, or going to the ground floor is to be given the access. That sort of judgments has to be there. That means we need to give some explanatory sort of thing. The abstract will speak only the superficial concept. That's all.
So we have to make like a presentation at the end of the project as well, right?
Presentation is must and should, along with your report and your result display.
Okay, that we can include that in the presentation only, or we have to make that separately?
Which one?
Like you said na that report and the results, we'll be including that in the presentation.
See, report is hard copy. Okay. Hard copy means I'll let you know what the hard copy should have. But your PPT will be having the explanation of your abstract, your description of the problem statement in depth, and how you have implemented and what are the results. Okay, that will be your presentation. Report will be the theoretical aspect of the total content given in the Word document form. Your circuit diagrams, your explanation, your introduction, your past approaches, or some past approaches if you have, and what is the idea that motivated you, why you have taken this idea, and what are the methods that are available, what are the advantages, disadvantages of this. Any sort of the explanation that is related, you have to put that in Word document. Then you will be giving the circuit diagram, implementation thing, and your output files of your this project printouts.
So, ma'am, like we have to print the screenshots of like the code and out. Is it like
Printout means, that means output files, you need to take the output files. After simulation, you will get the output files in your Verilog. That output files, you will be taking the copies, printouts of the output files, not
and
the
ma'am,
screenshots.
ma'am, can you give like what all have we have to write in the report as well? Like I'm clearing all the doubts now. Only I know it's like a long term process, but can you for once can you give us like what all we have to write in the report, as like it is our first project. We have never worked on such things before. So can you give
Yeah,
like an idea of
definitely.
what all we have to
Definitely.
write?
I'll share the content to your CRs. They'll share to you. Okay. I'll give what are the things that has to be like in a subtitle format. I'll give all the information. Okay.
Okay, ma'am.
Because if I dictate now, maybe you won't. You'll be getting confused. I'll give that as a like typed format so that you can follow that till your presentation.
And ma'am, the report, like only one person has to work on it.
No. That's what a group means, that in group you have to work in unity, something like sharing the work and working in unity. Both has to be done. That means writing the code you have to share. Say 4 blocks or 4 segments are there in your project. 4 students will be dividing each segment. Okay, each person will write a code of that segment. Say if that person is not able to write, maybe the other guy can help. Okay,
Okay.
in like that is something like we are training you to work in group, and how to divide the work for yourself so that you can handle that little bit easier, instead of taking it as a one big project and doing on by single hand. Maybe you are dividing the work and you are making it easy in working. But writing the report, presenting your results and explanation, everything will be in group. Each student will be contributing, each student will be explaining. It's not that one will be doing, one will be enjoying. No. 4 students are there, 4 students will be dividing the work. 4 students will be writing the code. 4 students will be writing the report. Okay. Report has different segments. Each segment a student can take up.
Okay, ma'am. Ma'am, my doubts for now are clear. For now, my doubts are clear, ma'am.
Okay. It's a group work. We are trying to get yourself acquainted. Group work. When you go to the industries also, they'll give you projects in group. It won't be a single person projects. No? In teams, you will be working. The teamwork you are getting acquainted here itself in mini project. Okay, I'll share the format of your report to your CRs.
Ma'am, just getting a point clear. So one group will be submitting one report.
Yeah, definitely, because
Okay.
that is only one idea, no? But writing the report completely should be distributed among the 4 students.
Okay. Yeah, fine.
But how?
Some writes regarding the explanation of first block. The second person does for the second block. That wise you need to do, and that should be what you say, consolidated into one report. After writing, you should consolidate that into a single report.
Yeah, got it now. Thank you.
Ma'am, about the consolidation part also, like how are we all are not like in the campus right now. How are we supposed to consolidate that work and all?
Yeah, I said, say blocks are there. Say first person will take up the first block scripting, and the second one will take for the second block, and so on. Na? Then what you have to do, you have to share that content among yourself and see that there is a continuity from each block to the other block explanation. And you have to group that into one total project flow.
Okay, ma'am. Yes,
And
ma'am.
the code portion also, 4 of you should be like, you should arrange yourself either a like online meeting sort of thing you have to arrange for yourself. You should have the discussion. You should have the conversation like how you are doing here as a group discussion sort of thing offline also. The same thing you'll do it in online also. Your interaction should be there. Without interaction, you may not complete the work. It is not possible. Say 4 of your ideas should be matching, and 4 of your content should be correlating and all. It should give you meaningful output now. That means you should be interacting constantly, discussing every stage with every other student. Say a boy who is writing a code for the beginning portion, a boy who is writing say middle portion, and the boy who is writing the final segment. All the 3 has to be compatible, and they have to be integratable. Something like the output of the first stage should be in a position to be integrated to the second, and second to be for the third. Then only it completes the work. No, when this can happen, when you have the interaction, when you are discussing yourself, like how to handle this, how to write, how to correlate, and how to get the output. Slowly you'll learn this. Say weekly, at least 1 or 2 days, you have interaction for yourself, have a group meetings, and discuss what you are doing and what are your ideas, how you are proceeding and all. Each and every student idea will be giving you one solution there. Have the group discussion, then you will be getting the final result. Okay. Yeah. Still any clarifications needed?
No, ma'am, not for now from my side.
Okay. Okay then.
Ma'am,
Yeah. Who is speaking? Rishabh Jain. Yeah. What is that query?
No, ma'am, it wasn't me. It was someone else.
Okay.
ma'am, the software which we have to download is Xilinx Vivado, right?
Yes.
Yeah, that latest version is 50 GB size, ma'am. Can we download other version also? Like
Even if a student.
2019 version.
Yeah, yes. Student version also you can download, because your circuits are very less complex to circuits. You are not taking a full system design, no? Student version
Yeah,
also.
ma'am. That 2021 version is 50 GB size, ma'am. It is so high, so can we use that 2020 version?
Yeah. Previous versions also you can take.
Yes, ma'am. That
For experimentation.
J-Link is not.
You see, updated version means few of the features will be added. Some features will be added, and like any say controls, you are not able to work out, maybe you will be going for updated version. Okay. For lab experiments, any version will support. Any version supports.
Okay, ma'am. For that latest versions, it took one day time, ma'am. Like for
Yeah.
downloading. That's why I'm asking like.
Yes, yes. It initially it will take time, and maybe it depends on whether you are taking the licensed version or a pirated version, sort of.
Okay, ma'am.
Okay. Okay then. Shall we close?
Ma'am, excuse me, ma'am. Ma'am, let's say I'm making something like a tube light type of thing, which takes input as number of people in the room, like you gave that an example. So how do I convert something like number of people into a Boolean variable?
You'll be using a counter. You need to have a counter, like practically if you take, that will be a sensor placed at one intersection point, either at the entrance or outside. At every intersection in one direction, we'll be trying to count up. Say the sensor which is placed at the outside of the door, it will be an incoming counter. A sensor which is placed at the inside of the door will be a down counter. Okay, that sensor pulsed initialization will be taken as a counter input. That counter output will be taken as the digitized form. No? You'll be taking that as count up or count down.
First I have to design a counter for that.
Ah.
So for how
As,
does the
as,
count?
as such, for your tube light control itself, you take, say you have 4 lights in your room. Okay.
Okay.
And the accommodation is, say, 10 people can be sitting in that room. So when you have only one occupant, 4 are not needed, only one tube light. Okay. So you can take the counter count. If counter count is minimal, maybe you'll be switching on one light. That means mux sort of thing. When counter full count is there, say, you'll be switching on the 4 lights. And if people are leaving one by one, you can automatically decrease the count, and you can switch off the lights also.
But the counter itself will have to take number of people thing as input, right? So how will that counter take that in?
Practically, I said, no, sensor and counter ICs will be interlinked. Sensor and counter. Sensor means actually an abstraction will be taken as the sensor input. IR sensors are there, no? What is the functionality of a sensor? How your sensor will work?
I don't know.
No idea?
No idea.
What is the functionality of a sensor? Sensor means it should sense, say normally IR sensors will be a sensor to abstract, like count the obstructions. A person crossing a door. Okay, you visualize the door now. First of all, you visualize the door. Okay, to your front side of your door, that means frame, there will be one sensor. So inside the frame, you have another sensor. 2 sensors will be used. Okay. The outside sensor, if it senses any obstruction happening, it will take it as a incoming candidate. So it will count it in up direction. A sensor which is placed inside, if it is taking a obstruction, it will take it as a down count thing. So you are using an up down counter circuit which will be having a control of the sensor output for controlling in up and down direction. You have read this up down counter, no?
Yes, ma'am.
So that up down counting will be, control signals will be the sensor outputs. You'll be doing that up or down counting based on your sensor output. Now, that count value, you will be tying that to your intensity control, like switching on your 4 lights, 4 switches, on off element. Okay, if it is equal to 5, 2 lights. If it is less than 5, 1 light. If it is more than 5, 3 lights. If it is full count, 4 lights. That way you need to write the flow. From that you'll be getting the hardware to control this now. Whatever the designs what we are writing here, say you can write your flow chart for that decision making. Even this ASMs and all, if you take, we'll be seeing how to write the problem statements. The next 2-3 sessions, you will be getting the introduction of how to write the designs in ASM. First, you find out the concept, then we'll think of writing about the code. You need to learn about writing the code. Okay? See,
Okay, ma'am. Thank you.
Single person may not be in a position to formulate the idea. You in group you have to discuss and you can formulate the idea. Formulating the idea also takes a group discussion. Deciding what to be done or what to be formulated is also to be discussed. Okay then. Yeah, if no queries, I'll close the session.
Okay.